Hello everyone, and welcome to Getting Started with Chip. Before we dive into the tutorial, I want to start by introducing you to the people who make research computing happen. First, our Assistant Director of Research Computing, Roy Prouty, Master's student, Bamlak B. Keel, PhD student, Raman Lolo Chi, myself, Max Breitmeyer, Daniel Esposito, who's an undergraduate in Information Systems, Hakeem Fessa, who is an undergraduate in Computer Science, and not pictured, but still very relevant, Tartella Debassam, Scales GA, who's a second-year PhD in Information Systems, and Rajarshi Basak, who is also a Scales GA and is a first-year PhD in Computer Science. And now we're going to go over the Getting Started on Chip page. This can be found under User Support and User Documentation on our website, hpcf.umbc.edu. And again, it's called Getting Started on Chip. This page is meant to help users new to the chip cluster get started, so you can follow along or skip to specific sections. Understand that this page requires some familiarity with Linux, but none with the HPC workflow, and will run through the basics of how to access the cluster, access research storage, run jobs, and load software modules. So let's start by just requesting a user account on Chip. If you had an account on either Tahi or Ada, you'll likely have an account available on Chip already, so you won't need to go through this process. But if you don't, as a faculty or staff member, you can request a new group or class. You'll just need to go through the actions listed here, mark research computing action as high performance computing, and then in the section mark HPC action, instead of user account creation modification, you'll just put new group type. For groups supporting classes, you'll need to provide the class name, but note that these groups are made to be cleared at the end of every regular semester and in consultation with the course lead. For groups supporting research labs, you'll need to provide a project title and a project abstract. By default, the group requester is automatically provisioned as a user within the new group, so you won't need to request that again. In the section marked research, if you're a student requesting to join a group, in the section marked research computing action, you'll click the drop down in high performance computing. Under HPC action, user account creation, existing PI, enter your PI's email, and then you'll put the project title and abstract that you're supporting. In the section marked subject, please enter any fields of research your project would fall under, and then in the comments or notes, enter any additional comments you'd like to know about your account or like to have applied to your account. Otherwise, you can just hit NA and hit enter. So now we're going to discuss accessing Chip. You're going to start by opening a terminal on your local machine, and this can be done in a number of ways. On Mac and Linux, command space and then typing terminal. On Windows, you can just hit the Windows button and type terminal. Doesn't matter, as long as you get to a basic terminal. I've already got one open. There are other ways to access Chip, such as terminal emulators like PuTTY, but for this tutorial, we'll just be going through the basic Windows PowerShell terminal. So start by typing SSH, your username, for me it's MB17, at chip.rs.umbc.edu. And it'll ask for your password. I've already got mine in. And then it'll hit you with two-factor duo authentication. I will go ahead and just type 1 for me, which will push to my phone. And I will hit accept and then approved. Now, do note that if you are already logged into the campus VPN, gpvpn.umbc.edu, you won't have to go through the duo authentication. So now that we're actually on Chip, we'll notice that you have your username followed by the host name, which is Chip. This is your login node, and we know it's a login node because it says @Chip. The login node is purely meant to be a place for you to land and interact with maybe a little bit of your data, but mostly interact with the cluster and its resources. It is not a place to run high computation jobs. Doing so can slow down the cluster and cause low performance for everyone else, and we as system administrators will have to go in and just kill those processes. So in general, just try to keep low computations on the login nodes. Simple commands like move, cd, maybe viewing your data. You'll also notice that when we logged in, we were given these 3 little prompts here, home directory, and then 2 research directories. Your home directory is always limited to 500 megabytes. It'll always say when you log in how much you have left, but you can also view it by doing home/, df-h home/mb17, or of course your own username, and it'll again show the same thing. And then also how much space is left in your research directories. Now I'm part of 2 research group, DoIt and Don Angle, so it showed the total output of both of these. We can also directly go to them by checking our aliases. So we have, as the system administrators, have automatically defined certain aliases based on what you have. So I'm part of DoIt and Don Angle, as mentioned before. So I have DoIt_Ada, DoIt_common, and DoIt_user, which all leads to the various paths that you should be familiar with: UMBC, RS, DoIt, and then either common or users/your username. Note that in your user area, this is your private space. No one else can touch it except for you and your PI. No one else should have access to it. The common space, and I'll just show, right, like this says UMBC, RS, DoIt, users, MB17. The common space is for any space that you and your group are working with in a collaborative space, right? And then also there is the Ada storage. This is only relevant to you if your group has had an Ada storage in the past. You should check with your PI to see if it exists, but just to show, UMBC, Ada, DoIt. So that's how you access these research volumes. You can always double check where you are by typing this command, pwd. It stands for present working directory. It's worth noting that these research volumes, they are shared among your common and your user, so they're not separate. As shown in this little diagram here, if your PI has 1 terabyte, that is shared between your common and all the users. They are not separate. Your home directories are separate though. Now let's talk about actually accessing these resources. To access the resources, you need to use a program called Slurm. And Slurm is a scheduling program used by many HPC facilities designed to make sure jobs are run in the most efficient manner. At a high level, Slurm works by a user telling Slurm what specific resources they need, cores, time, memory, GPU cards, etc., and Slurm putting that program in an environment with those resources available. All of this is done from the login node, which we have shown is can be seen just by making sure you're at chip. Chip CPU and chip GPU have slightly different requirements when putting in a Slurm request as described here. The basic Slurm commands that you'll need to know are srun and sbatch. Srun is a command that allows a user to run an individual commands on compute resources. Using srun can allow users to start interactive jobs, which can also be helpful for development and testing of code. Sbatch is a command that takes a bash script as its input and executes the series of tasks using the compute resources. Functionally, these commands do the same thing. Which commands you use boils down to preference and need. Additionally, you can find some information about the status of jobs or nodes using sinfo, which we can see here. Would split into the cluster of chip CPU and chip GPU. In general, you're going to see one of 3 states: idle, mixed, or allocated. Idle means no one's using that node. Mixed means some of the resources are being used but still has some available. And allocated means that the entirety of the node's resources are being used and Slurm will not attempt to put any new jobs on it. SQ can show all the jobs that are running on the clusters. In general, there's going to be 3 states that you're seeing here. There's pending, which we can see here. Running, meaning the job is currently running, and completing, meaning the job has finished and Slurm is cleaning up any remnants from the node. Now, how do we actually access these resources? Like I mentioned earlier, to do it for chip CPU and chip GPU is going to be a little bit different, but at a high level for chip CPU, if you were to run an srun command, you would need the cluster, which equals chip CPU. The time, that's the amount of time you think the job will run. So let's say 10 minutes, that's what it defaults to. The memory, which defaults to 500 megabytes, let's say 500 megs. The partition, we'll just say that's the general partition. And the general partition is anything in the 2018 or the 2021 nodes. The QoS, which stands for quality of service, and that determines how long and how many CPU resources you think you're going to take. We're only taking 500 megabytes. CPU is only 1 core, and our time is 10 minutes, so we'll just use short. And the account, and for that we'll do pi do it. And then of course the actual command that you're going to run. So let's do hostname. Let this run, and you'll see that it spits back C1822. And of course we can put any other command there, but hostname is just an easy one to show. And again, you can also copy this command from over here. So if you can see from above, I am telling Slurm to run on the chip CPU cluster, right? I'm using 10 minutes of time, 500 megabytes, the general partition, QoS short, and I'm telling it that my account this should be run under the pi do it count. And remember that account is specific to the group that you're a part of. And then of course the command that I'm running. Now, if I were to submit this as a batch job, what would it look like? Well, let's go ahead and create one. We'll start by using our favorite text editor. I prefer Vim, so that's what I'll use. We'll do sbatch test.slurm, and it'll open up a new thing. And I'll just go ahead and copy what's in the test on the page. And again, you're going to see that at the very top, you should always tell it's running bin bash. This is called the shebang. And then you're going to give it the slurm directives, which is the same thing that we saw before. I've changed it to time is 1000 and QoS is long. And then we're still just going to ask it for a host name. But this can be any series of other commands. We can say echo hello world, sleep 5, and then host name again. And it'll do all of those things for us. So now we've written this into an sbatch file, and we're going to just run sbatch test.slurm. And so we've seen that this is now submitted on the cluster. If we were to run sq-u mb17, it's already finished. So our job already finished, and we can see that we have a slurm.out file associated with the job number that we submitted. So we're going to look at slurm.169.out, and we can see again the host name hello world C2104. Now let's go ahead and discuss how to use chip GPU, which is basically going to be a similar thing, but it has slightly different syntax. You're still going to need cluster time and memory, but you're also going to need a generic resource, and you're no longer going to need a partition or a QoS. So what does that look like? Let's just run srun --cluster equals chip GPU --time equals 10 --mem equals 500. And again, these default to minutes and megabytes respectively, but you can specify them in other ways. And then we'll need the generic resource, which is long for GRES, equals GPU, and then the number of GPUs that you want to run in the environment. We just need one. So then we're going to go ahead and give it the command NVIDIA SMI, which is just a normal command for checking the statistics on a GPU that you're using. So we're going to run that. And chip GPU is generally under a little higher load, has fewer nodes than chip CPU, so it might take a little bit longer to run. And now you can see that after a moment, NVIDIA SMI ran and gave us an L40S node. Now we can do something similar with our sbatch. So let's go ahead and create a new file. Let's call it GPU sbatch.slurm. And we'll put in the same things that we did before. Spin bash. And welcome back. So now you can see that I've gone ahead and created a similar file to before, but again, we didn't need that account partition or QoS. I've gone ahead and put hostname, NVIDIA SMI, sleep for 10 seconds, and then hostname. So if I exit out, saving this file, and I sbatch GPU sbatch.slurm, Okay, we can see that we've submitted the batch job 69334, and I can do an SQ-U MB17. And we can see that our job is not running yet, but it does have priority as soon as there's availability. So we'll give it an interval of 5 seconds. It has started running at this point. And so the next time it runs, it should be just about finishing up, 10 seconds. And when it shows again, it'll be gone. Great. And so we're going to again look at the file that's associated with our job number. That was 69334. So let's check our slurm. Yep, there it is, slurm -69334. Let's cat that out. And we can see that we were put on G2402 NVIDIA SMI-RAN, and again, showing G2402. So now we're going to talk about the different modules and softwares that are available on the chip cluster. Many different pieces of software with different versions and dependencies are all available to use on the chip cluster compute resources. Users may interact with the library of software modules via the module command. In order to keep the login node performance and accessible, software modules are not loadable on the login node. You can see here attempting to load a module on the login node will result in a note saying that it just doesn't work. And I'll show you live just to make sure everyone's on the same page. Right, and we get the same thing. I would highly recommend checking out our additional information on the LMOD system, also known as the module system. That's this module keyword here. We have documentation here. So there is different software on different nodes. And how do we know this? We can check using the keyword module avail, and then we'll just look at some piece of software. Let's look at Git, right? We can see that there are 3 different sections. There's the core and custom modules. There's the for use on 2018 and 2021 machines, and the for use on the 2020 and 2024 machines. Now, we know that the core and custom modules work on all computers, all nodes, regardless of partition, cluster, it doesn't matter. For use on 2018 and 2021, these only work on the 2018 and 2021, right? And then for use on 2020 and 2024, only works on 2020 and 2024. These are not cluster specific, okay? These are computer architecture type and purchase year specific. So these work on all of chip GPU and the 2024 partition of chip CPU. These only work on the general partition, i.e. 2018 and 2021 of chip CPU. And then again, these work on all the nodes. So we're gonna go ahead and just look at one of these on a compute node and what it looks like to actually run these different nodes. So we're going to start an interactive job. We're going to do srun -- cluster equals chip CPU, time equals 10, mem equals 500, partition equals general, QS equals short, and account equals PIDoIt. Now we're going to do one special thing that you haven't seen before. We're going to add this PTY at the end, and we're going to put shell, right? And this tells the cluster, the Slurm scheduler, to start an interactive job. We're going to go ahead and run this, right? And now we can see our bash prompt has changed. We're no longer on the login node, but instead we're on a compute 2021 node, specifically node number 4. All right, and so now if we look at the module avail Git, right, we can only see the 2018 and 2021 and the core and custom modules. We can no longer see the section that was described as for use on 2020 and 2024, which makes sense based on what we described earlier. The same thing can also be used for chip GPU. So we're going to do another srun, but we're going to do cluster equals chip GPU -- time equals 10, mem equals 500. We don't need to do a partition. We don't need to do an account or QoS. We do want to put a GRES. Let's say GRES equals GPU 1. And again, we're going to put this little PTY at the end that says shell. Shell. Right, and we're going to sit here and wait for a second. And we're back in G2402, right? And so if we again do this module avail Git, we can now see that it's showing the core and custom modules, which is expected, but also the 2020 and 2024, but not the 2018 and 2021. There's more information about all the different softwares and how to search it in that LMOD LMOD link that I showed earlier, as well as how you can use Python on chip and more. So I hope this was helpful for you all. And as always, if you have any issues or questions, please send a ticket to RT, and happy computing.